Hey, Thomas.
Hey, Luca.
All
How
right.
was?
Yeah, things are busy, and we've been doing a lot of detailed discussions on distributed or auto diff and transformer engine. And one of the danger of when you do all these things is like, how do we things work? Like, where do we stand in performance land, and do things actually work when we put them together? And so today we thought about like making a point and see where we are with the kind of stock Qwen and LLaMA 3. LLaMA 4 is an MOE, so we'll get into MOEs in the near future. But let's say LLaMA 3 and Qwen, very popular models. How are we doing compared to if we take unoptimized code and then throw what we have at it? Will we have any speed ups? Will we slower than eager, faster than eager? And then what do all the pieces that we have, like FSTP, our own distributed, and so on, compose to make things run fast on machines? And since we are in the next generation architecture land, we said, why don't we test it out on a B200 machine? So this episode will feature a B200, Qwen and LLaMA, and a bunch of things like cuDNN, SDPA, transformer engine, FSTP all together, and let's see what performance we get out of that.
Yeah. So more precisely, it's the 8 times B200, right?
Yeah, it's the 8 B200s that are available on Lightning Studios, and so that's why we have the luck of being able to run on those.
Right.
Before we get into that, I just wanted to mention something that when I went to PyTorch Paris, let me share my screen for a split second. Here. When I went to Paris for PyTorch Day, among the people that were talking, there was a deep speed person from Snowflake, I believe, and they presented all the things that they have. And among the things that they have that are new, there is this deep compile. And deep compile, I like the project a lot because right now it's more of an experiment. So it's and I hope we will collaborate in the future. But it makes the perfect case for things like deep compile and Thunder to exist. And this is what they say basically. Distributed training has become essential for scaling today's massive deep learning models. And then why deep learning compilers like PyTorch compiler dramatically improve single GPU training performance through kernel fusion and scheduling. They fall short when it comes to distributed workloads. And so deep compile addresses this gap by enabling compiler level optimizations for distributed training. And so it takes a standard single GPU model implementation and transforms it into an optimized multi-GPU training graph without requiring changes to model code. So thank you, because this kind of validates our strategy. We are not just about distributed. We also take care of the other pieces, so we're kind of more holistic in that sense. But I think, it kind of reinforces the fact that as we move forward and things become larger and architectures become more demanding in terms of like knowledge you need to pour into optimizing them, the need for compiler level optimizations that enable all these different things, including distributed, is coming out pretty clearly. And I think this blog post from DeepSpeed summarizes why deep compile and Thunder exists. So if you guys want to take a look, please take a look, and then I'll give control back to Thomas here.
Yeah. So then let's see where we're at, right?
Yep.
So it's the B to 8 times B machine.
Fancy.
Yeah, and I like it a lot. And the thing is, you wait a while for it, but there's a new button here, auto switch machines, and it's like super cool because it will turn on the machine and not like, oh, your machine had been ready, but now it's gone again.
Yeah.
But of course, you still need to like watch the thing in order to not like pay for the fancy machine, and you're like doing other things.
Yeah, I'm
But
curious, how long did you wait for it, by the way?
I think it said 7 minutes, and it was about 7 minutes. So
Yeah,
pretty
it's
good.
not too long. Yeah, exactly. So if anybody wants to try out B200s, like you can get it in little over 5 minutes.
I mean, they're not super cheap. The H200s are like half the price, but yeah,
Yeah,
they're pretty neat, and they're also like 7-8 minutes wait currently.
yeah,
It varies during the day. Like I
yeah, yeah.
had go to 3 minutes, and I had this go to 15. And but yeah, you
Very cool.
know what you're up to. We don't bake these machines, but so we have to just say what we're up to.
Yep.
Okay, so we have this little benchmarking script that we've been using a lot currently, also because we like wanted to know where we're at before we submit the abstract for the PyTorch conference.
Aha.
Uh,
It's
yeah,
ready. It's ready. Just ready to be clicked and submitted.
yeah, and so I still have the thing that the libraries want to be found, but so here's a torch run invocation, 8 nodes, and we're using FSDP distributed, and as a baseline, we will just take llama 8 billion, and then with a block size 8K, and run it with Torch Eager, right? Which is,
Is there a typo in distributed mode F? FSP?
I think it's just like a thing where it,
Oh, the rendering. It's a rendering problem. Yeah, yeah. Okay, okay.
funny.
Maybe not. Maybe yes.
We will see. If
Yeah.
not, like it will
So
not work.
just to summarize, this is a llama, right? 8 billion
Yeah, from the
coming from LGPT or Hugging Face.
it's LitGPT.
Okay. And context size is 8,000, so it's a pretty substantial context size. The task is pre-training, right?
Yeah.
And we're using Thunder's FSDP implementation that we looked at some time ago.
No,
And
here
this
we're
runs, yeah.
for the eager we're using, of course, like the PyTorch one.
Oh, sorry, this is eager still. Yeah, I
Yeah.
didn't realize. Okay, this is eager. So this is PyTorch's FSTP. We're not saturating RAM. We could increase the batch size, but for now, let's keep it that way. We're not saturating memory, but we are 100 gigabytes. So
Yeah.
luxury of going with the B200. Like, nice. All right.
So
Okay.
here we are. We get 700-ish iter times.
Yeah.
And one of the things I did this week was stare down these things. And one of the things we did was hunt down like what attention module has been used. And so if I compile this with Thunder, we see that it takes a few minutes up front, but then we see that it's faster. But one of the things I did was I installed the cuDNN frontend. After we looked at the traces, you can also dump the traces for forward and backward from the benchmarking. And then these traces basically showed that we were not using cuDNN attention. And
Yeah.
so obviously, like these NVIDIA libraries, they bring a lot of value. So this is here the main things are cuDNN and also the cuDNN attention and the and the NVFuser fusing all the things, right?
Right. So basically, we're running. We are trying to fuse with NVFuser. Some operations will be maybe still PyTorch eager, dispatch to eager, maybe. I don't know.
Things like
Possibly.
embed, probably.
Yeah, exactly. And then we have attention, scalar.product attention that will be dispatched to Qwen and SDPA, which is
Yeah,
not
and
usually the case when you use, eager, PyTorch eager, and should help because here we have a context of 8,000. So it's like a substantial context.
right. And so the other thing to know here is that the other thing that goes to PyTorch eager is the linears, right? Because we're not
Yeah.
using anything special here, and PyTorch eager will dispatch it to kublas, probably.
Yeah, and linear in general, I mean, PyTorch does a very good job with linear. So if you don't have to fuse it with anything right after, then I think linear has been optimized to death. I don't know how many kernels are there within PyTorch eager to, that are dispatched based on heuristics on the shapes and so on. So it's just not one kernel. There are many. I don't know how many.
Yeah, and of course the other part here is that the linears are the main part of the runtime. So before flash attention, the attention operations were the
Yeah.
long stuff, but with flash attention and all the developments from there on, you have that the linears actually take the majority of the time.
Yeah.
Okay, so one thing that's pretty neat is that the memory used has
Oh, yeah.
decreased.
Yeah, it was 93 before, and now it's 79. Yeah.
Yeah, and so this is one of the things. The other thing is the average iteration time, like has gone up. It
Oh,
has
wow.
decreased quite a bit. So it used to be
700, 690. Yeah.
yeah, and so that's quite a good
That's,
speed up.
yeah, pretty crazy speed up. Yes. And a lot of it just experimentally because we did some more experimentation, but a lot of it actually comes from the flash attention kernel that
Yeah,
is in Qwen. That makes a ton of difference. Yes.
I could deinstall the Qwen and then
No, don't do it.
yeah. So the other part is that we can layer the next thing. We just discussed that the linears are the slow part, and as you know, the linear is a cubic operation in the shapes,
Yep.
and so it pays to actually do the quadratic operation in the shape to convert the matrices to a lower precision and then execute in lower precision. And so
Mm-hmm.
this is what a library called Transformer Engine that we have mentioned a bit over the last few sessions too. And so this speeds up the linear by computing it in 8-bit. And we can just run it here and see what
Yeah, and
happens.
this is faster because the architecture, like it will be faster on H100 and 200s too. But the FP8 implementation has been improved in the Blackwell. Because otherwise, like if you had to kind of simulate FP8 support in preview, like an Ampere, that would actually like maybe consume less memory, but be slower because there would be some.
It wouldn't help with the memory either, likely, or at least not
Yeah,
much.
because you would, yeah, not much because you need to
Because
store the
at
weights
least,
in
right,
uncompressed form. Yeah,
at least currently it would not. Uh,
yeah.
so what the current transform does is it replaces the operations one by one with things that convert to FP8, run the thing, convert it back. So I would imagine that there would be potential to also like reuse some of these things, just put it on the model.
Right.
Um, and also, Transformer Engine has many more functions like
So yeah,
distributed things like that.
Yeah.
And so it will be interesting to see what we can do with, if this is Transformer Engine V2 executor, then maybe that will
There will
be
be
a
V4, V5.
good way.
Yeah. I mean, you get a lot for free, right? Because something we got for free is support from MX FP8, for example. Like Transformer Engine is very much onto next gen architectures, and so yeah, we'll see what effect it has. By the way, something that we didn't mention is that before, when we got from 700 milliseconds per iteration to 450 milliseconds per iteration, that thing went from FSDP from PyTorch to FSDP from Thunder. So the
Right.
distributed that we just ran, the previous run, was handled completely through the Thunder FSDP transform that we wrote and we showed you in the previous episodes, that you find in the code base. So that's nice because it all composes together. And yeah. Interesting. And we shaved another 100 milliseconds, and now we are at 350.
Right. And
Yeah.
From 700 to 350, that's about a factor of 2.
And another 5 gigabytes in memory saved, by the way.
Yeah. So
nice. Yeah. I mean, that's significant, right? And one of the significant things is that we started from a single GPU implementation. That is like the standard GPT, but we also tried with Hugging Face implementation. Numbers are not exactly, but very, very similar. And so you start from something serial. You don't have to do anything to it. You go through transforms and you go from 700 milliseconds to 350 milliseconds just because you start reusing things that pertain to the how and not the what. That's beautiful. I think it's great.
Right. Yeah. And that is something we see also for other models. So we could like do the same 3 things for Qwen now. We are using the Qwen 2.5, and and we see similar scaling, right? And so it seems to be that for the transformer-based architectures, which are like not all that different between one and the other, it seems pretty consistent.
Yeah, and maybe let me share plots that you.
Let me stop sharing instead of leaving.
Yeah, exactly. And also, you should stop the B200. Just saying. Yeah, it's not cheap, but it's cheaper than buying one. So
well, so let's say our friends at NVIDIA don't want us to say expensive, but it's
no, that's fine.
An exciting budget if we're doing this too long.
Yeah, it's true. I'll take it back. Let's see. Where's my window I want to share? Oh, here. Nice. All right. Let's see if I can do it. So we compiled a few scenarios here. No, it doesn't want me to do it, unfortunately. How can I do it? One sec. Let's the results. Oh, here. I see. All right. So here are the results that we got across the board. We compared to Torch Compile, but it's not like that is just a sanity. So don't take it as, oh, Torch Compile is so slow, blah, blah, blah. It's not. It's very fast as well. As you can see, if we compile the models using Torch Compile, sometimes we're slightly, and without any extra stuff like Qwen and Transformer Engine, sometimes and so you need to look at so the blue is our baseline, just eager. And then in the first column, the first stack of boxes, here you have LLaMA three, on H200 from Hugging Face. And then on the red column is us with just MVFuser as a Fusion executor. And this is Torch compile with Inductor as a Fusion executor. And then the next is now we add the Qwen executor as TPA, the first example that we ran. And this is all with FSTP from Thunder. And this is when we layer on a transformer engine. And then when we do the same, always Hugging Face code base on B200, this is what we get. And it's all relative to the baseline, which is H200 Hugging Face on eager on the H200 machine. So this is, in the end, if you're running with all optimizations on a B200, you're getting 3 times as fast compared to the H200. Yeah.
And the other thing is that if you compare these numbers, if you just switch to the B200, you get the 1.5 Vish speed up.
Yep.
And if you do it for the optimized things, you get a 2x speed up approximately, right? You go from 1.5 Vish to almost 3.
Yep.
And that's a pretty neat thing, right?
Yeah, it tells you that, as we were pointing out a few episodes ago, that the more next-gen architecture you get, the more you need those optimizations in. Otherwise, you're better off staying with the previous arc, right? If you compare this blue line to the green line here, just use the libraries, right? On a previous architecture, right? So it's really something. And of course, there are ways to use Transformer Engine and Qwen with Torch compile as well, and with using compiler flags. The beauty, I think, on the Thunder side is that all these are basically transforms, so you can layer in more things. So it's an extent. This is your starting point, essentially. And then if you want to do more things to, like, for example, what deep compile proposes, and I think we will probably take some inspiration for future iterations on our distributed stuff. They kind of optimize according to the memory profile. They optimize when they prefetch, something we already discussed. And so this is your floor. This is not your endpoint. This is where you start from, and then you can layer in more transforms. That's the whole gist of the thing. All right. Awesome. So that's a good checkpoint. I mentioned MOE because MOE has some specific challenges. You did some work on MOEs, Thomas, a couple of months ago, right?
So one thing, of course, you can do, or the specific thing on MOE is that you suddenly have shapes that you don't know ahead of time. And that is very tricky for a number of things. Mm-hmm. The first thing tricky with is Thunder itself, but we could work around that. But then you have the CUDA graphs, and for the CUDA graphs, it's tricky again because they essentially require constant memory pointers and also constant thread layouts. And so essentially all the parameters to the kernel calls need to be fixed. And so one thing to do in Thunder, of course, what you can do if you leave aside the CUDA graph things for a moment, one of the things you can do is you can just wrap the entire thing into one big symbol, and the output of the MOE layer will have the same shape as the input, and so what happens in between, who knows? Yeah. And this is one way to route around it. And the PyTorch colleagues, actually, they published a blog post what they do, and they have one variant where you do a lot of things, it pays to just pad things as needed and run statically, and then they have a dynamic version too. So there's still people are figuring out how to do it, and it's not really clear is it best to fix it on the tooling side? It could be also that you can do something with the modeling. But it will be interesting, and it will be a challenge to represent that neatly without making it a huge black box, right? If your Thunder trace run model, then it's
Yeah.
not interesting. If it is CUDA graph and then a lot of operations, that will be much more interesting. The other thing I wanted to mention here, in addition to the blog post, is that there was this blog post from the
Thunder
Thunder Kit,
Kittens. Yeah, I knew that. Yeah. Yeah, the
and
mega kernel.
the mega kernel, they essentially, like, as far as I understood, they more or less put all of one of the small llama models
Yep.
into one big kernel. And this is the advantage that you can like stay in shared memory if you want and stuff like that. The detail there is that you need to essentially, yeah, this one.
Yep.
Hey, Research is the official name, not the Thunder Kitten people. Um, and so one of the things that they do is they essentially, or one of the first things that you need to do is you need to fix the thread layout and block layout that you're using throughout the entire thing.
Yeah, exactly.
But you will only have one kernel launch, and so it needs to be the thing that does everything. And then they need to do things like uh, you need the output to be finished before you can work with it. And this becomes more tricky. Usually it is by when a kernel terminates, it has done all the stuff it did, including the writes, and the next kernel can assume that it was done. And if you want to have more detailed patterns, then you need to handle that synchronization.
Exactly. And
Um,
they do it using, yeah, in this section, they do it using an internal counter. So basically what they're doing is they're implementing some kind of like interpreter that runs within CUDA that interprets all the kind of synchronization stuff. I think it would be pretty interesting, and maybe uh, there is a path towards facilitating acquiring a model, maybe using Thunder and doing something like that to facilitate at least some part of the process. I don't know.
Yeah, it will be not easy, but
Right.
tricky. So one of the things is that there's sometimes you meet people that say, "Well, I wrote my own library from scratch and playing CUDA,"
Hmm.
um, and so I sometimes wonder whether it would be worthwhile to have something where you actually try to have your individual kernels also follow that pattern, that you
Yeah.
have one launch configuration and then you pass in all the metadata like the shapes. They're
Hmm.
usually kept on the CPU, but you put them on the GPU instead, and then the kernels can run independently on what the shape of the input is. And
Mm.
that was super cool in order to be able to CUDA a lot of things that are currently not CUDA.
Yeah.
And so that might be
Yeah, that might
interesting.
be the thing.
If
Yes.
Obviously, PyTorch has like 2,000 different kernels, and it's a lot of work if you want to do it for everything. But it might be interesting to have some of that too.
Yep. Well, nice. That's super intriguing. So anybody who wants to get more in the weeds, like happy to get you on the Thunder repository and experiment. I think we're getting there, and I think the episode today kind of proved the point that like there are very concrete advantages. So thanks a lot, Thomas, and yeah, it's gonna be a long weekend in Italy, apparently, because it's the Day of the Republic on Monday, and so probably I'll be at the lake as usual. You'll find me there.
Very good. You have a good weekend at the lake.
Nice. All right. Bye, Thomas. Bye, everyone.
See you, Luca.